Welcome. So my name is John Osama. I'm here at the National Conservation Training Center in Shepherdstown, West Virginia. And welcome to this edition of our web series in partnership with the National Climate Adaptation Center through the U.S. Geological Survey. And today's webinar is titled Climate Projections as a Way to Illustrate Future Possibilities. And we're excited to have Adrian Newton from Oklahoma University with us today. To introduce our presenters, we have Laura Thompson, who is a research ecologist at the National Climate Adaptation Science Center. Laura, take it away.
Thank you, John. It's my pleasure to introduce for today's INCAS seminar Dr. Adrian Wooten, who is a postdoctoral research associate at the South Central Climate Adaptation Science Center. For nearly 10 years, Adrian was a student researcher at the North Carolina State Climate Office and worked closely with the Southeast Climate Adaptation Science Center on projects involving both scientific research and stakeholder engagement. She earned her PhD in atmospheric science in 2016 from North Carolina State University and joined the South Central Climate Adaptation Science Center in 2017 as a postdoctoral research associate. At the South Central Climate Adaptation Science Center, or CASC as we call them, Dr. Adrian Wooten's research focused on the accuracy and uncertainty associated with climate modeling and downscaling, with added emphasis on the use of climate projections in impact assessments and decision-making. She also works with the tribal liaisons and other South Central CASC staff in outreach and extension efforts to help ensure that research meets the needs of stakeholders across the South Central U.S. Adrian is also the editor-in-chief of one of the founding members of the Early Career Climate Forum, which works to promote communication and collaboration among graduate students and early career professionals in climate science and related disciplines across the United States. Adrian, we're very happy to have you, and I will hand it off to you. Thank you for being here.
It's my pleasure to be with you all. I thank you for the invitation to present this afternoon. The climate projections are powerful tools in climate adaptation planning, and they can tell us many stories of how the future climate could unfold, illustrating many possibilities that we could have to adapt to. What I'm going to do today is to give a little bit of understanding first on the climate projections and stories they tell, and why there can be so many different stories and possibilities that come from the climate projections. Then illustrate a bit from my research on what this means for projections of precipitation in the South Central United States, and then talk a little bit more at the end here about what that would mean in terms of impact assessments and decision making, and some of the things that users should take into consideration. So on the first hand there, of course, when we're talking about climate change, we're talking about changes in the measures of climate persisting over many decades or longer. And measures of climate, we could be talking about the average annual temperature or the frequency of extreme temperatures or extreme precipitation. And all of this is well and good, but why do we worry about understanding a changing climate? Why does understanding a changing climate matter? A changing climate changes the frequency of droughts, which then we have to consider what does that mean for ecosystems and agriculture across the United States and the livelihoods of the people therein. It changes the average high temperature, which could mean potential detriments to human health for multiple communities across the United States. It changes the frequency of heavy rain events, which again presents another challenge for protecting life and property, as well as protecting infrastructure maintained by the federal government. And perhaps on a more subtle level, it also changes the length of the growing season, or changes the timing of first leaf and first bloom, which, particularly for USGS and interior interests, presents challenges with phenology and ecology with regard to the management of our natural lands and different endangered species. So all of this, of course, leads to the want and desire that has been increasing in the last 10 years in particular to have climate projections available for use and assess the impacts of a changing climate across the United States and indeed increasing globally. So this is projected change to the annual average high temperature here in Oklahoma City. And I should say this is one projected change. one future story that could unfold. This goes all the way out to 2100 and shows the change in temperature in degrees Fahrenheit. Now, this would be great if this were the only climate projection we had. It'd be something really easy to plan for, right? You know, it's going to increase by about 6 degrees Fahrenheit at the end of the century. That's great. One item to work with, but would it be the right thing to do? In reality, in working with the climate projections, what we really have is a picture that looks a lot more like this for Oklahoma City. This actually comes from a collection of climate projections produced in-house here at the South Central CASC, of which that one black line in the middle is a single member of that set of projections. And so we have many future storylines for how the climate could unfold. The interesting thing here, of course, is if we plan for just that one in the black, then does that potentially leave you vulnerable to something worse? An increase of up to 15 degrees Fahrenheit by the end of the century, according to one of these particular storylines, is a possibility. And that leaves the concern of just planning for one story is not necessarily the best way to do it. But looking at the many stories that the climate projections can tell us and being able to plan for multiple scenarios that could be good or could be really bad. But of course, the question that I then get next is, okay, why are there so many different future storylines? Why do I have to deal with this particular mess that we have to work with? There's a few different reasons for that. And the first of those reasons is human action, or the hope, or trying to represent what human action will be at large globally. So, society at large, we have multiple options for future action with our own development as a society, as a planet. From continuing with a higher emissions to changes to less intensive energy sources and sustainable development. These societal choices are reflected in the climate projections through what are called representative concentration pathways. The RCP here 8.5 reflects a situation where there's continuing higher emissions of greenhouse gases. On the other hand, the RCP 2.6 here represents a situation where there is a decrease in emissions or a sustainable development or a rapid increase in technology for carbon capture, for instance. RCP 4.5 here is the middle ground. The information from the RCP was provided to the climate models, which then describe for us how the climate would respond to those human actions. And so from that whole map of storylines we had before, we have at least 3 now to work with based upon just that information with the RCPs. The interesting challenge then is there are actually many climate models that exist. This particular map has one circle on it representing each of the different modeling centers that has produced a climate model for the Intergovernmental Panel on Climate Change assessment reports. In fact, I think this is a little dated now because there's more centers that are now contributing for the 6th assessment report, which is upcoming. But to date, all in total, there's more than 40 climate models that exist. But why do we have so many climate models when we actually have a really great understanding of the fundamental physics of the climate? Why do we have so many of these? To understand that, I think it's important to go back to what is a climate model to begin with. The climate models are built now, I think it's almost 150 to 200 years of scientific research and fundamental physics that describe the atmosphere, the ocean, chemistry, physics, thermodynamics. These equations with the fundamental physics include things like conservation of mass and momentum and energy, and then also things down to describing surface temperature and surface precipitation. All of those equations are converted to form that computers can solve, and then solved for a grid over the entire planet to then give us projections of temperature, precipitation, and much more, going out across the globe to the end of the century and increasingly in the assessment reports for IPCC beyond 2100. When I'm referring to a climate model, often what the formal name is, we call them the global climate models. And these are mathematical representations of these many physical processes in our world. They work by dividing the planet into an immense grid of boxes, not just in X and Y, the latitude and longitude, but also on the vertical, up into the atmosphere and down into the ocean. For each of these grid points, then, the model calculates all of those equations representing all of those physical processes going out through time. It's a massive computational effort and often uses an intense amount of supercomputing for all these physical interactions and processes. The interesting thing here, of course, is that with all of those physical processes involved, we can get back to why do we have so many different climate models to begin with. We have a great understanding of the fundamental physical processes behind the climate, like the greenhouse effect and the interaction with those greenhouse gases and the atmosphere to begin with. But there's also many more processes represented in the global climate model than just that. In fact matter, everything that you see in this graphic is represented in one form or another in the global climate models. Everything from the formation of clouds to the interaction between air and ocean to wind and volcanic activity. And it's in all of these different smaller processes that are so important that we find the reason why we have different climate models. While we have a great fundamental understanding of the changes to the climate and why the climate is changing, there are some processes that we don't completely understand yet. And as a result, there's competing theories for how each of these individual processes work, which lead us to different equations representing those physical processes, and each of those equations can be used to create a new model. Now, that might sound like a little bit of gobbledygook, but let me give you an example of what I mean using clouds. So I'm going to say right up front, these are not real papers. Please do not cite them. They are not real papers at all. This is just an example of what I mean by what can happen with a physical process and competing theories. So let's say Smith in 2003, after doing a lot of observational work and modeling work, looking at cloud formation, determines that there is this particular physical relationship between cloud formation and temperature, represented with this particular constant. That gets published into one paper, and that could be incorporated in one climate model. On the other hand, you may have Jones, who comes in a few years later, and then based upon their work, trying to add to that theory behind cloud formation, or with their own theory on cloud formation. Jones comes in and says, no, I think the actual relationship is something more like this, with a different constant involved. Both of these are valid theories for cloud formation, and until one theory is disproven or another, they could be both used in the representation of cloud formation in different climate models. This is a really simple example, but cloud formation is actually a pretty important process because it does affect temperature here at the surface and also the values of precipitation. So there's more actually than just two different theories on cloud formation and different physical processes there, and particularly with respect to convection and thunderstorms. But there's also many, many, many other processes in this graphic where this is the case, and some of these small physical processes that are very important to the climate. So if we go back then to our data for Oklahoma City, suddenly now I've added a few more red lines to these, and each of these are from a couple of different global climate models. And which one do you work with? Now there's a couple of different stories in here that you could go with. The German model says one thing a little bit warmer for this area in Oklahoma City, whereas the National Centers for Atmospheric Research model here in the United States, they're suggesting perhaps a little bit cooler future than the other one at the very end of the century. So that's another reason why there's so many different stories in the projections. If you think about it, we have 3 RCPs here at least, and there's more than 40 climate models to work with. There's potentially 120 stories there to get started. Increasingly now, there's also the question of whether or not one needs local information. On the left-hand side is temperature output at a typical resolution for a global climate model. And what I mean by resolution, for those unfamiliar, is the spacing of the grid in the model. These are about 200 kilometers apart. These are 200-kilometer wide boxes. And what you can kind of tell if you look at this image is that it's very pixelated over the United States. It doesn't give us a whole lot of detail. Global climate models, by their nature, run at the global scale and produce information globally, but because of the computational expense involved, they can't be very fine everywhere. They can't give us the beautiful detailed picture of what's going on locally. That would require a tremendous amount more computing power to be able to do that. But the thing is, we know there are physical processes that aren't going to go away, that happen at a local scale, but they're not going to go away when the climate changes. For example, we know that the temperature changes dramatically with elevation. So here in the Rockies, there should actually be some more dramatic changes in temperature than what you see here. You also kind of can't see the Appalachians at all in this particular section. Another particular physical process is that there's a temperature relationship between, there's a relationship between temperature and the proximity to coastline, to the ocean and water, to the ocean. But that's not really visible in here in the model either in here or over here, or anywhere along the Atlantic coast either. What we really want for more applications purposes is a picture that is a bit more like this, where you can now see the dramatic changes in temperature with elevation. You can see how Florida shows up much more clearly with temperature over land compared to the ocean surrounding it. You can finally see the Appalachians in this particular picture and where they are based on the temperature. To get from what the global climate model looks like to a picture that is more useful perhaps for adaptation purposes and studying local effects to climate change, we use a process called downscaling. And downscaling translates the global climate model's change to the local scale and reincorporates all the physical processes that we know are going to be there, or I should say the effect of all of those physical processes that we know will be present in the future. And indeed, this is actually a downscaled climate model output at roughly 25 kilometers between all of those little grid boxes. I should say 25 kilometers now is one resolution, but there's actually some publicly available data now that provides results at 6 kilometers, and much even finer than this. The interesting thing, though, is just like there's competing theories for different smaller physical processes in the global models, there's also competing theories for the best way to approach doing downscaling and that translation to local scales. And as a result, there's not one downscaling technique that is preferred or the absolute best in all situations. And as a result, if we go back to Oklahoma City one more time, we can see here now that suddenly we have many more lines on here, and I've added about 3 or 4 downscaling techniques on top of the global climate models that I put in here. So now we have RCP with global models with downscaling techniques involved. There's much more information to work with and many more stories. And if we put it all together with the other 2 RCPs, we get back to that picture that I showed you at the beginning and why we have so many more storylines in the projections than just one to work with. And this is great because it does give you a range of possible futures to plan for. And it comes back to what kind of risk you're willing to tolerate as a decision maker and what you want to explore as the worst case impact if you're doing an impact assessment, or maybe the best case of an impact. Now that I've provided you a bit of a grasp on some of the reasons why so many projections exist and so many future stories can be told, I want to get into some of the more subtle details that can change the storyline, particularly for precipitation. To describe that, though, I'm going to have to give you a little bit more detail behind what downscaling is and show some results from my research in the South Central United States. There's 2 main types of downscaling, one of which is called statistical downscaling. Statistical downscaling works by training a statistical relationship here between observations in a historical period and a global climate model simulation during the same historical period. Once that relationship is trained, then it can be applied to the global climate model to then give us an estimate of what those observations would look like. In a historical period, we can look at this and see what the skill of our downscaling technique is, but with respect to the future, we can apply that same statistical relationship to the global climate model projection, and that gives us then an estimate of what the future observations would look like. The interesting thing for us now in the world as we are doing downscaling, in the statistical form of downscaling, I should say, is that we are not using weather station data for the most part to do this, not directly anyway. We are using what's better called gridded observations, and these are interpolations of weather station data. And we do this in part because we want to overcome some of the limitations of weather station data. Weather stations are not spatially complete, for one hand. They're dots all over the United States. But perhaps we want some information on how the climate is going to change in a particular park or in a part of South Texas or somewhere where there's not a weather station data. To do that with statistical downscaling, one could use the gridded observations as they have interpolated the weather station data across the United States. But just like the statistical downscaling techniques themselves, there's not one approach to doing the creation of the gridded observations. And as a result, now there's several different sets of gridded observations available publicly, and several of them have been used to create publicly available projections including those used in the 4th National Climate Assessment. The other thing, of course, as I already kind of hinted at, is that the downscaling techniques are not standard. There is not one standard choice because we have competing theories for what works the best in our particular efforts to do that downscaling and translate global change to what it means in local scales. But the important thing in all of this then is that the global climate model is one input, the observations are another input in here, and the downscaling technique is the third choice to make in this particular collection of information I'm going to talk about. But all three of those have an impact on the raw precipitation data, but can also have an impact on the change signal for precipitation. In other words, some of these little subtle details can change the story of the future climate, particularly with respect to precipitation, quite dramatically. Let me show you some data to illustrate one of my points, because I'm sure everybody's thinking observations. Well, aren't all observations a bit of the truth? Can we just use one and have it tell us the same exact truth all the time? On the top here, we have 3 global climate models, and they're a simulation of the historical climatology for annual total rainfall across the south central United States. This is in millimeters, and we know they're not perfect, absolutely, but we can also see how they capture pretty well the gradient of precipitation across the south central United States, from wet on the east side to a much drier area in New Mexico. And we can see this particularly in comparison to this bottom left panel, which is one set of gridded observations that is referred to as DayMet. But now we add another set of gridded observations in here. They look very similar on a first glance, but can you tell perhaps that there are some subtle things that may change the story just a touch in particular places, particularly in New Mexico, where it's already very dry as is? Or we could go further to another data set. This one comes from Oregon State University, the PRISM data set. Can you notice here something a little subtle with the changes in precipitation? It doesn't look like much, but maybe it does matter if we're using these things in downscaling and changing the story of future precipitation just a little bit. So all of this is a lot of itty-bitty little details. Most of the time it's people like me who do a lot of downscaling and evaluation of downscaling that really care about this. But why do I care about these things? I think about this with respect to impact assessments in particular, because changing these kinds of subtle details can affect the timing, frequency, and the amount of precipitation that is coming out of each of these kinds of projections. Changing that story just a little bit and then providing it to an impact assessment, it may mean quite a difference in what the projected impact is of a changing climate. It also then affects our derived variables. To get to extreme precipitation and drought, we often produce projections of daily precipitation and then derive from that the changes to the precipitation extremes or changes in drought. And the other reason I look at this is making sure that we have all the information that we could possibly need and want to provide for the proper use of the projections in multiple other applications. Now in the next few slides, I'm going to get into some of my research results, which are actually part of a paper that's in review right now, and show you some of these things to illustrate my point. So this is a set of box plots. On the left-hand side here are the 3 gridded observations and their representation of the annual total precipitation across the south central United States. The 3 box plots in the middle here are for those 3 global climate models that I showed you before, and their representation of the annual total rainfall during the same historical period. And the final 3 box plots here are actually the future rainfall from those 3 global climate models out at the end of the century. This is 2070 to 2099 here at the end. And I should say right up front, these come from simulations done with the RTP 8.5. Now, what I want you to take away from this in particular is that, okay, sure, there's some differences there in the annual total rainfall, but it's not all that much. You might get a story here that's actually pretty similar. There's some subtle differences between the global climate models and some subtle changes with respect to precipitation, or at least it looks subtle. I'm going to show a few maps a little later that might emphasize a little bit that the change is more than it looks. But in the aggregate, there's little difference between the gridded observations for annual total rainfall. This is absolutely not the case for variables related to precipitation, as I can demonstrate right here. This is the same set of box plots, but now this is for the annual number of rain days, or the number of wet days for the south central United States. Do you notice something interesting here? The set of the LIVNA observations here has many more wet days in it compared to the DAYMET and the PRISM gridded observations. In the analysis, we've actually found that in some cases this is up to twice as many rain days compared to the other two gridded observations. The global models here have more wet days than the observations and also suggest a decreasing number of wet days as you go forward. So that part of the global models is pretty well known actually in literature, and I'm not going to dwell on it too much today, but if you're interested, you're welcome to ask a question about it later. And downscaling works to correct a lot of those particular features. But this is something that's been lesser known. Why are the observations here so different? All of these are things that we would consider, air quotes here, the truth when we're doing downscaling or evaluating our modeling work against observations that could be used for that also. Why is the LIVNA here so different? To get to that, you have to go back actually pretty far to when the observations are created before we even do interpolations of weather station data. So the gridded observations make use of both automated and volunteer station data. The automated data is, as you suggest, as it would suggest, technologically driven. They automatically report, and electronic sensors and the whole works there report their totals, report their 24-hour totals of precipitation at midnight. The volunteer stations, though, on the other hand, are manned by people, and people don't necessarily want to be up at midnight to report a 24-hour total of rainfall. They'll be happy to get up at 7 o'clock in the morning and do that, but that means their 24-hour total is from 7 a.m. to 7 a.m., not midnight to midnight. And that creates a temporal mismatch between volunteer stations and automated stations. Both are used to create gridded observation data sets, and so that is one particular mismatch that can be accounted for when gridded observations are created. Some creators of gridded observations do actually account for this, but others don't. Or they take a different approach to the one that the LIVNA observations do. The method that we use to create the LIVNA data set splits the rainfall total over 2 days. And this increases the number of rain days, but also decreases the extremes. Now, let me walk you through a little bit of an example, because this might make absolutely no sense at first blush. Let's say we have an observer that on 7 a.m. on day 2 reports a total here of 1 inch. What the adjustment here would do is that, knowing that there's 7 hours in the second day, in that overlap there, we take 7/24 of that 1 inch of rain and can keep it on day 2, but would rather keep the other part of that rainfall, the remaining large amount of rain, on the first day. And so before that adjustment is done, the observer record would look a little bit more like this, where on day 1 there was no rain, day 2 there was 1 inch of rain reported by the volunteer. But after the adjustment and before the interpolation of the weather station data, you could also see something, you would see something more like this, where now suddenly there's almost 3/4 of an inch of rain on day 1, but 1/3 of an inch on day 2. In the aggregate over 3 days, it looks exactly the same. But in that 3 days, now there's 2 days of rain instead of 1 to work with. And this affects the increases the number of rain days I mentioned, and it also decreases the extremes. So this is all well and good, but now it's time to see, does this actually have any effect on the downscale data? Does it change the story at all when we get to the end with the projections? This is the same box plot as I was showing you before. This is the annual number of wet days for the historical period, but I'm going to start revealing a few things here for you. These are the 3 observation data sets again right now. These are the number of wet days in the 3 global climate models that we are using. These are 9 sets of downscaled climate projections, 9 possible stories to work with, and what they now show for the number of rain days during that same historical period. And of course, can you tell now which set of observations was used in each one, how the story is just a little bit different? These are climate projections produced here in-house, and in part because we were interested in exploring this research question of what does it mean when you change the gridded observations when you're doing downscaling and providing that to users. But as I mentioned previously, there's many different downscaling techniques that exist and many different sets of now downscaled climate projections available publicly. So my wonder for this as I was preparing this talk and a couple of others was, okay, can we see the same feature in some of the publicly available projections? And the answer here is that you can. These are actually data from same global climate models, but two different other downscaling techniques that, were used to create a set of publicly available projections, not just for the South Central U.S., but also available for the rest of the country. And I'm going to highlight this one in particular because this is actually 3 global models from the LOCA statistical downscaled data set, and that is the data set that was used in the 4th National Climate Assessment. And so this is why I bring this up in terms, and just to have it as something interesting. So the story there with LOCA is perhaps a little bit different if LOCA had been created using a different set of observations. So both the observations and GCMs are used in downscaling, and they're both very important inputs. But to that end, it's also important for us to realize that the story can change a little bit because the downscale projections will inherit any of the unique features from the observation data that's used. We've seen this now in the raw data, but I think it's a good time to go check what does this mean in terms of future change. If the same issue is there in past and future, does it really change the potential how much rain will change in the future, how much it will decrease or increase, or how much the number of days with rain will increase or decrease? So this is a little bit complex and busy. Here, let me walk you through this. What you're looking at in the box plots on the right is the projected change now, not the raw values, the projected change in the annual total precipitation. This is the end of century, 2070 to 2099, compared to our historical period of 1981 to 2005. This is, again, for RCP 8.5 based simulations. The 3 box plots here on the left-hand side are just for the global models by themselves. No downscaling done to them just yet. The 18 remaining here are from the projections done in-house here at the South Central Climate Adaptation Science Center together with our partners at the NOAA Geophysical Fluid Dynamics Lab. They're grouped here by the observations that were used. So you can see this first 6 are from DAMET. Then they are subgrouped by the different downscaling techniques. And for the sake of time, I'm glossing over a little bit what the exact downscaling techniques and things are, but you are more than welcome to ask me in the comments section. In the comments session, rather. The big thing I want you to take from this particular set of box plots is that it doesn't seem to matter for this particular variable what downscaling technique you use and what observations are used. What seems to matter more in the story of the projected change of total rainfall is what global model is used here. This is further emphasized if you look a little bit more at some of the individual simulations, like this particular map from the from one of the global climate models compared to this particular downscaled version, one story, of the change in total rainfall across the region, compared to a different downscaling technique across the same region. They're about the same. The story didn't change there as much as it changed across the global climate model. And it was the case for just the raw data. This is not true for other variables, and particularly the number of wet days. Can you tell how much the story is very different just going across those set of 18 box plots now? Suddenly there's a range from quite a decrease in the number of days with rain to, in some places, a dramatic increase in the number of days with rain. This is the same layout as, I should have said that first, this is the same layout as the previous slide, but you can tell now there's much more spread in here in the stories told from the projections. This is also reflected when you go back into the map, particularly changing story, changing downscaling techniques changes the story quite dramatically. So this is for that one particular global model showing a pretty strong decrease in the number of days with rain in the future. But this is that same global model downscaled with one particular downscaling technique in here, which shows about the same to actually a slight increase in the number of days of rain across the domain. But if one switches to the other downscaling technique that we have, then the story becomes a bit different again. And we go back to having a decrease in the number of days of rain across our domain in the future. And this is a pretty interesting issue when we're talking about how do you plan for these kinds of things, if this is an important variable for you. There are other variables where you can see some similar issues. I have some few things on extremes up the road that will also be quite interesting for you all. But the thing here that also makes this graphic very interesting is what we talked about with the gridded observations doesn't go away when you move into a projected change. For example, if you look at this particular box plot here in the green, this is for one global climate model downscaled with one technique, but using the DayMet observations in there to provide the training data. But then if we flip over here to using something with the LIVNA training data here in the orange, you can actually see how there's such a difference in just switching what observation data was used. And that goes back to that, I think at least goes back in part to that feature where LIVNA has twice as many rain days in it with smaller amounts of precipitation in general for a given day. That makes it very interesting. You change the gridded observations used, you change the future story at the same time. Something very subtle and simple. In the real world, we recognize now that some variables that we're really interested in for adaptation and planning might be very sensitive to the choice of downscaling technique and gridded observations that are used. The annual number of wet days being a really good example, but it's not the only one. Others, though, are not so sensitive. Annual total rainfall could matter, doesn't really matter entirely what set of observations you use, what downscaling technique is used. It's all about which RCP are you looking at and which global climate model are you looking at. But you might have noticed in this particular plot, and it's still the annual number of wet days. I just added a few things in there that you can't see right now. The projections I've shown you thus far are from our in-house projections here at the South Central CASC, but I want to add back for you those projections that are publicly available. And this one in the red is, again, the set of projections available from the LOCA, which was used in the National Climate Assessment. And so you can see there's a spread of story that is still continuing there with the different sets of downscaled data from the public versions. It gets to be fun when we start giving maps to users and talking about what does it mean in projected changes. So for instance, we go back to annual total rainfall again. We have in here all of those 18 that I showed you all averaged together. And then these two different maps here on the right are averaged together by the different downscaling techniques that we've used. Hey, not all that much of a difference there again between downscaling techniques, just to make a point of emphasis here. That doesn't mean there's no spread in the stories. And I apologize, there's so many little mini maps this may be hard to read, but the point that I want you to take from these is that you can see there's some variation there across the individual 18 members. And anything from quite a bit of increase in rainfall over in here in the eastern part of the domain and in this one to dramatic decreases across much of the domain. The picture gets a little bit more different when we talk about the annual number of rain days, where we can see, okay, the total mean gets a bit muted, but that's in connection with the difference between these two different downscaling techniques, with one method showing a slightly less of a decrease in the number of days of rain in the future on average compared to the other method. And this goes back again to looking at some of the individual members and picking out the stories. The scale in this is actually a little bit different. This tops out at a decrease here of more than a month fewer in rain days in some of these simulations. So ask a question for those of you who might be watching from this particular region. What would you do if you had a month fewer days of rain to work with? A month or more where it was dry? What would you do actually if you were in Louisiana, knowing you guys had just had a quite an intense rain event with Barry passing not too long ago? What would you do if you suddenly had many more days with rain to work with? I mean, both of those are possibilities in here. Both of those are stories that could unfold. I didn't talk about it much with the box plot, so I figured I'd leave you with something a little interesting and different. These are the annual one-day maximum rainfall projections. So think of your heaviest rain event of the year, how much heavier it could be, or as this one downscaling method would show you, how much less it could possibly be across the region. So that's an interesting story. What would you do if you had your heaviest rain increase a lot, or would you be happy if suddenly the heaviest rain events decreased quite a lot in the future? How would you plan for those two very different options? Or what would you want to plan for? What would be the worst? You can see this reflected again in the individual members. I'm not going to, in the individual stories, I should say, I'm not going to belabor the point with this, but what would you do in a situation? This is actually the scale in these little ones actually tops out at an increase of 60 millimeters or more in some of these. So take your heaviest rain event and add another 2.5 to 3 inches to that particular rainfall event. What would you do if it was much heavier, essentially leading to more flooding events? So my point in all of this is that one projection is only one story. And it's not necessarily the wisest thing, depending upon what you need as a user, to look at only one story. But the projections provide us many stories that we can use for planning. Depending upon what you need, you need to look at a lot more, perhaps. Annual totals, it's about the same. You probably just need to look at a couple of different global models and a couple of different RCPs. On the other hand, occurrence and precipitation extremes can vary pretty widely. So that's kind of important. If you're worried about a drought situation, occurrence is an important aspect. If you're worried about flooding, extremes would be pretty much of interest there. What does all of this mean, perhaps, for impact assessments? So we know the choice of downscaling technique now and the observation data can affect the raw daily precipitation, can also affect the change signals for precipitation variables. And it's interesting for me in particular when I'm working with impact modelers now to that a lot of them use daily precipitation as an input. Ecosystem hydrology models in particular, crop models do make use of daily, raw daily precipitation and temperature projections as their inputs. And so I am wondering at the moment what some of the impacts would be and how some of the stories would change if we gave many more stories that were connected to different observation data and different downscaling techniques to those modeling efforts. I'm hoping actually to find that out soon with another project that I'm working on a little bit with the New Mexico Water Science Center, taking some of the same projections that I've shown you and running it through the PRMS hydrology model. Looking forward to seeing what they come up with to changes in water supply and runoff and stream flow along the upper Rio Grande, I should say. But I'd love to see more if people are interested in exploring that. So I would also include, I also like to include a word of caution, because climate data can't ever tell you everything. The projections here can tell you a lot of the future storylines of how the climate can unfold for many different things at this point. But they can't tell you anything about how risk tolerant you are. The projections can't tell you anything about how vulnerable your systems, communities, species, anything that you may be interested in are to the changing climate. Thinking back to all of those pictures at the beginning, I can't tell you how much your community would be vulnerable to an increase in extreme heat. I can't tell you how much your community would be vulnerable to an increase in heavy rain events or an increase in the frequency and intensity of droughts. I can't tell you, nor can the climate projections tell you what the changes, what would it mean to change the length of the growing season or first leaf or first bloom to species that you're interested in. But you all know these communities and systems the best. Those of you who are in management or doing impact assessments, you know these all the best yourselves. And so it's always good, I think, based on the stories that the climate projections provide, to ask those what-if questions. If you suddenly had 60 more millimeters of intense rainfall in your heaviest rain event with more flooding that could happen, what would you do? What would you plan for? How would you approach handling that situation? Would it be really detrimental or really good? You may know that, and if you don't know that, that's actually where climate scientists can also be of help, is helping you figure out, is your community actually really vulnerable to that or not? Community or system or whatever you're managing really vulnerable. Hey, would it be great for you if the extremes of precip decreased? That's another option. How would you approach those kinds of questions? Now, with that thought-provoking discussion on how you might plan for some of these many different stories, I think we can shift into taking questions. If you want more information on the climate projections that I showed that are in here in-house, I would ask please email our info@southcentralclimate.org. Particularly if you're in our region, we'd be happy to work with you on getting you access to those projections if you're interested in using them.
So we have a few questions right now, and for those of you who are still in the webinar, feel free to just throw them into the Q&A box. We'll get through them all. The first one comes from Robin. She asks, challenge of dealing with the imperative to consider multiple future storylines. as she so ably articulated, can be addressed in practice by using scenario planning. Okay, so it looks like a little bit of a statement. Thank you. Scenario planning explicitly forces one to consider multiple options. Good point. David can you talk about any thinking on the best approach today to the main challenge you're highlighting? Possibly averaging or better selection of reanalysis data sets to find the best one, and what would that mean?
Mm-hmm. Okay, I see the question now. Let's see, not counting RCPs. So the way that we've approached this typically in the past has been to, because we understand, okay, 3 RCP times 120 global models times 30 plus downscaling techniques that exist times however many gridded observations, that becomes completely unmanageable from the user perspective, or unfeasible to work with. So what we have often recommended, and I think continues to work well, and meshes a lot with the scenario planning, is to, working with a climate scientist, look at the possible spread of the storylines and select a few out of those which would work well for your planning efforts, 3 to 5 to, I think 3 is the minimum we ever suggested, but 5 to 10 or more, depending upon what you're capable of working with. But doing that in conjunction with a climate scientist or one of the boundary organizations. I do like averaging in the sense of you get a good glimpse or snapshot at what the sort of average change would be, but I don't recommend it using just that, because you could be ignoring the extremes in the worst case scenarios for the system that you're trying to manage or the impact that you're trying to assess.
Next question comes from Ryan. Is it fair from your analysis to conclude that we should maybe avoid LOCA and other downscaled projections that are trained on LIVNH if we're looking at precipitation metrics other than annual mean?
Hi, Ryan. Let's see here. I've been hesitant to recommend LOCA knowing this right now. I don't think it's necessarily a bad thing, because it's not the projected change there is not outside the realm of possibility. So from that perspective, I don't completely discount it, but I have not also seen yet what it does in the context of a hydrology model, something trained with LIVNA does with that, and that's what I'm kind of concerned about, stream flow projections in particular. So I kind of caution it, but I don't say, I don't think it's necessary that we avoid it altogether. I just place a caution flag there instead of a penalty flag.
James says, at Edwards Aquifer Authority in Central Texas, we are beginning a 5-year process to assess how changes to temperature and precipitation may affect our aquifer recharge over the next several decades, and our plan is to use downscaled GCM projections. So the presentation looks like it got cut off. Sorry about that, James.
I'm going to say you're in our domain region, so you'd be welcome to email us if you want to work with us on that whole process.
Oh, there it is. So I see the second half of it. He's asking, can you recommend contacts? So that kind of answers that question. So Marissa, thanks for the great presentation. Your research looks really interesting. As a scholar, what type of activism have you been engaging in to get your science heard by non-scientists?
I actually haven't been putting myself out there as much, with the exception of doing presentations and being asked then to do more presentations like this, not just to scholars, but to non-scholars and non-scientists around the region. So I have not gotten a huge amount of activism. That said, the one way we did advertise was mentioned in the introduction that I am the editor-in-chief of the Early Career Climate Forum. And that's one way we've been advertising has been through that forum, otherwise known as the ECCF. So if you have any early career students who are interested in connecting with other climate students, other students working in climate or postdocs working in climate across the country, please feel free to email me about that. I can put them in connection there with that, but I have not directly done any activism.
Thank you. Angela has a question. What kinds of graphs do you find practitioners are most receptive to? For example, are people most receptive to box plots, scatter plots, maps, or something more creative?
That's an excellent question, because it does depend a little bit on the level of knowledge that some users already have. Because in the general public, I think a lot of people like maps, so we tend to use a lot of maps with that, and that has done really well. We actually had this conversation not too long ago, helping a couple of our tribal nations in the region prepare some climate adaptation plans of their own. They actually did very well with those maps, also with some bar plots that we worked with them, showing them that. What we found is that with all the different stories there, if you're willing to work with people and help explain it to them, they tend to get it. People do understand that there's more stories there than one, and it's just a matter of working with them to help them understand how to use it. So yeah, maps have easily been some of the best to work with alongside box plots. We haven't done a whole lot of scatter plots actually, but yeah, I think maps have been the favorite. Seen a lot of people be really receptive to that.
Great. And Ashka, I hope I said that correctly. Have you looked at any drought variables, particularly low-frequency, persistent dry events, in the context of uncertainty from downscaling methods?
So have I looked at drought variables? Indirectly, yes. So in the paper, we have also looked at the length of the longest dry spell and the length of the longest wet spell. And there is effect there also from the observations and the downscaling techniques. I don't have that in this presentation. I'm happy to share more of that with you if you'd like to email me. But I should say also, we haven't looked directly at the drought indices like SPEI or SPI yet, though that's something we've been planning and considering doing.
Okay, thank you. Looks like that's all the questions that we have. Well, thank you, Adrian, for your presentation, and thank you to everybody that participated today. This was a great webinar. I'd once again just like to thank ELDA and USGS for their continued support of this this webinar series. And
John, can I add one more thing before we go?
Absolutely.
So what I just wanted to mention is that one thing to be clear on is that not all the downscaling techniques and the observations are equal, and sure, so depending upon the circumstances and what you want to use it for, some things may be better than others. So that's why it is really important to work with CASCs and with the different boundary organizations. So we'd welcome having that interaction with you, which is why I also put our info@southcentralclimate.org email up there. So if you're in our region, please feel free to contact us through that also.
Great. Thank you very much, and everyone have a nice day.